Okay, so the other thing that we talked about last week was we started to talk about, and we're going to continue to talk about, is simple harmonic motion. So simple harmonic motion occurs whenever something is being restored to an equilibrium point um, by some force. The example that we looked at was a spring mass system. So mass system. Again, you already have these notes. I'm just trying to give you another little review of it because that's what I would have done if I could see in person. So in the spring mass system, the restoring force is the spring force. So we have the force of the spring equals Kx. Force of the spring measured in newtons. We have the spring constant, Newton per meter. And then we have the x is the distance from equilibrium, how far it is from the equilibrium point. So if this is my equilibrium point and I pull it back, the force gets stronger and stronger, and it's always pulling towards that equilibrium point. Even when it passes that point, it's pulling back towards that equilibrium point. And so we get motion that kind of looks like this if we think about a mass on a spring. So if I take this spring out here, let's say this is A, say this is x equals A, x equals 0, so it's right here. And then let's say x equals negative A, be about right here. Okay, so if I pull this mass out this far, the force would be pulling back towards equilibrium. My velocity would equal 0. So this is at point A at a different time, B, it would be moving towards the equilibrium point. At that equilibrium point, the force is equal to 0 because the x would be 0. So the total force would be 0, but it would be moving with a velocity, and that velocity would be the maximum speed that it would be moving. It would be at that equilibrium point, and then C now the force would be moving back towards that equilibrium point, and the velocity there would be 0. So it goes from 0, speeds up to this point where it's the fastest, goes past equilibrium point, going towards negative A, slowing down till it reaches that negative A. That's when it would stop momentarily, for instantaneously really, and then start moving back towards that positive A. And it would just keep going back and forth between these two, A and negative A. All right, so if we do a XD graph of the motion of that mass on a spring, you would start at a positive A, move to 0, negative A, back up to A. And so we get that wave function. This would be negative A. The time that it takes to complete this wave, this time t, would be our period. So from here to this point here, that would be our period. Big T, remember, is our symbol for period. So from A, positive A, to 0, from here to here, that would take 1/4 the period. From 0 to negative A, from this point to this point here, would be 1/4 the period. From 0 to, from negative A back to 0, that would equal 1/4 the period. And then from 0 to positive A again, that would also equal 1/4 for the period. So that can kind of help you decide at what time is the mass at a certain position. Because if you know the period, then you can divide that into fourths and you can figure out, is it at A, 0, negative A, 0, or positive A. Just knowing that it takes a fourth of the period to do each one of those travels. So we also looked at the factors that would affect the period of a spring mass system, how long it takes for it to complete a cycle. That would be the period. So we were trying to figure out, well, how can we change how long it takes for this cycle to be completed? One of the things we said was if we increase the mass. So if I increase the mass, then the acceleration would go down and it would take a longer time to complete. So it would increase the period. So an increase in mass would increase the period. Then some other people said, well, what if we change the amplitude? If I stretch it farther, then it has farther to go. And so the assumption is that if it had farther to go, that it would increase the period. What we found was that it didn't do that. Because when we stretch it further, then we have a greater force, greater acceleration, so the mass will be moving faster, and it's going to balance out or cancel out the distance, the extra distance that it has to travel. So increase in amplitude has no effect on the period. The other thing was change the spring constant. Remember, that's the stiffness of that spring, how much that spring is pulling. So if we increase that, if we increase the spring constant, we get a greater force, get a greater acceleration, and then that would decrease our period. So putting all those things together, we came up with an equation for the period of spring mass systems. The period would equal 2 pi times the square root of the mass divided by the spring constant. T, again, is the period. It's measured in seconds. M is the mass. It's going to be measured in kilograms. And then K is our spring constant. Measured in Newton IE. Newton per meter. So that's what we reviewed the week before spring break. So I will be posting new videos soon. So see you then. Bye. Hello. So I'm going to do a quick review of what we did right before we went on break. So what we did, we started with waves. So I'm just going to really quickly just review. This is stuff that you already have in notes. So we have wavelength, lambda, which is just the length of the wave. We have frequency, lowercase f, which is the number of waves that pass a point in a second. That's going to be measured in per second, 1/2, or hertz. All of these are the same. By the way, this is also just measured in meters. The other thing that we need to know is the period. This is big T. This is the time for a wave to complete one cycle. This is measured in seconds.